Our next sense is the sense of hearing. So we've talked about sense of vision. So vision is our main sense. Next one would probably be in the lineup, hearing, just because we are tying that usually to our vision. So the range of human hearing is limited. So there are actually lots of frequencies that we are unable to hear that other organisms on the planet are. You may already be familiar with the fact that, for example, cats and dogs can hear sounds that we can't. And so the range of human hearing is limited to this range, 20 to 20,000 hertz. And not all of us can actually hear that range. So I'm actually going to pop this open. And this is going to play through those frequencies. Ooh, there we go. So you can see we started at 20 hertz. And what you're listening for is a hum. Generally down here at the low end. Most people by now can hear it. So I'm going to bring it back down, because if you can hear it there, now you'll know what you're listening for. So we'll start back down here at 20 hertz. The line that you're seeing, that is the frequency graph. So remember we talked about sound and waves. So that is the wavelength and amplitude being graphed out. So you can see it changes as we go up. You'll also get some resonance when the waves build up on each other. That's why you get the little standing waves where it looks like they're crossing each other. So you definitely should be able to hear it by now. And I'm not changing the volume. It's going to sound louder, but it's not getting any louder. All that's happening is that the frequency is increasing, the pitch is increasing. And we are more sensitive to the mid-range here of our hearing than we are to the low and the high. So this middle section is going to sound very loud and very annoying. You can see the wavelengths are getting quite short. And you may notice that it kind of goes in and out as far as how loud and how annoying it is. And that is tied to your own personal hearing. And we'll talk about how this is working. You may notice now that the wavelengths are getting so close together that it's almost impossible to tell them apart on the screen. I can tell you I can't hear it anymore, but my guess is that most of you can. Okay. So let's get back in here. So anything that's below that 20 hertz that we started at is what we call infrasonic. So infrasonic is below 20 hertz. And you can't hear it, but you can feel it. So you've probably experienced below 20 hertz, or even if you can't hear 20 hertz, you've felt 20 hertz. So very often you'll feel this kind of like as a beat almost in your chest. And that actually is what's happening. The sound waves are moving the air that's in your lungs. And so that's why it feels like something's hitting your chest. Things like avalanches, earthquakes, volcanoes, meteor strikes, those can all create infrasonic waves. So I'm hoping that none of you have been in those kind of events, but they all are natural sources of infrasonic. We also can create, and sometimes do create, infrasonic for parts of our music, mostly so for that feeling of, that jar. Animals use infrasonic for communication, specifically these guys right here, whales, elephants, and hippos. This is why we sometimes don't hear them speaking with each other. However, we can tell that they are communicating with each other. Now with our equipment, we can record the sounds that they're making and make them audible for us by, changing the frequency a little bit so it's up in our audible range. But they do make these noises, and that makes sense because infrasonic can travel farther. The wavelengths are longer, and so they can travel farther distances, especially in water. And so for whales and hippos, this works really well. Elephants, this is actually the reason why, this is one of the reasons, there's two reasons why elephants have such large ears. They actually have these large ears, one, so that they can cool off, which is probably something that you've already kind of been familiar with. But the other reason is they need the large ears in order to be able to catch these infrasonic waves, these big wavelength waves where they're communicating with each other. So they have this big surface area in order to catch those incoming waves. Ultrasonic is the other direction. So infrasonic below 20 hertz on our hearing range. Ultrasonic is anything above 20,000 hertz outside of our hearing range. So other animals can hear ultrasonic. This is usually why your cat or dog has gone bonkers, because they can hear ultrasonic. Other animals use ultrasonic. So for example, mice often will make noises in the ultrasonic. And so if you ever have, your cat just sits there and starts doing the, in the middle of the floor and then goes kind of crazy, like they've been touched by, another dimension, it's probably because they can hear ultrasonic and you can't. And so they're hearing a mouse or a chipmunk or something making noise. They also can communicate with ultrasonic or use ultrasonic as a tool. So for example, bats actually use ultrasonic, and they use that to hunt. They use it for echolocation. If you could hear bats actually scream. It's kind of funny if you think about it, because they're actually flying and screaming in the ultrasonic to use their echolocation. So they're sending out those sound waves in the ultrasonic and having them bounce back at them so that they can create a picture. So bats don't have very good eyesight, but they have excellent hearing. And so they're using those sound waves bouncing back at them, but they have to send them out at high volume. But we don't hear them screaming because it's too high out of our hearing range. We also use ultrasonic in our technology. So we use ultrasonic in radar. So using it, for example, being able to find ships underwater or to be able to map the bottom of the ocean. So we use the same idea as the bats. We bounce the sound down, and then as it bounces back, we capture the differences in the sound, and that gives us the shape of the bottom of the ocean. And this is actually how we get ultrasounds. That's why they're called ultrasounds when we are looking at, for example, pregnancies, but also you may have had an ultrasound done for if they were looking at some structure inside of your body. I had an ultrasound done several years ago. They were looking at my gallbladder. Something small that won't show up on an x-ray, but you can look at with an ultrasound, because the sound waves in this ultrasonic, the high end of sound waves can actually be used to bounce off of structures to create pictures using our machinery. All right, so let's talk about how we hear. So we're going to do the same sort of thing with how we hear, like what we did with vision. So we're going to trace the pathway. So we're going to start on the outside. So sound waves come in, and they're going to be funneled in through this structure called the pinna. Yep, this part of your ear actually has a name. So the cup part of your ear is called the pinna, and that works as a funnel. And it's going to point the sound waves into the center part of your ear, down the canal to your eardrum. And your eardrum is called the drum because it vibrates like the skin on a drum. So as the sound waves hit it, it's going to vibrate back and forth at the frequency of the sound waves that are hitting it. Then it's going to transfer those vibrations to these guys back here. And so there are 3 tiny bones behind the eardrum that the eardrum is connected to. So the eardrum is going to vibrate. It's going to transfer that vibration to the hammer. And then the hammer is going to vibrate the anvil, and the anvil is going to vibrate the stirrup. These are actually the smallest bones in your body. So the hammer, anvil, and stirrup are the tiniest bones in your body and the ones that are responsible for your ability to hear. So we've got our sound come in, it vibrates the eardrum based on the frequency and the amplitude, because sound is also based on amplitude for how loud it is. So that gets transferred, the frequency and amplitude gets transferred by vibrating the hammer to the anvil to the stirrup. And these guys also amplify the sound. So they're going to actually make those vibrations stronger as it travels through, because we're going from air to solids. First a solid membrane, but then we're going into solid bone. And so remember, materials that are solids have those molecules that are close together, and so they vibrate and transfer sound very effectively. So they're going to amplify and expand that sound as they move through that bone. Then those vibrations will be transferred to what most people call their inner ear, or the cochlea. So that is this structure right here. It looks like a snail shell. That's the easiest description for it. So the stirrup is connected to the cochlea, and that is going to be your inner ear. And we are going to talk about how that structure works in the next video. Before though I end this one, I do want to point out why I have this random diagram attached to this slide, because I'm sure some of you are looking at it going, what's going on there? So this is showing you something that most people don't realize. Some of you may actually be able to wiggle your ears. Unfortunately, I am not able to wiggle my ears. Obviously, I can make my ears move, like when I smile. A lot of people can do that. But some people can actually wiggle their ears independently, up and down and maybe a little bit back. The reason why you have that ability is because we all have these muscles that you see attached on this picture. And these are actually what we call vestigial or leftover structures from our ancestors. Think about like a dog or a cat, or really almost any mammal, right? They have the ability to move their ears. Primates are one of the few that can't really do it anymore, and that's because these muscles have gotten small. So these muscles were actually in charge of being able to turn our ears towards the sound so we didn't have to turn our head. In fact, if you attach electrical monitors to these muscles and play sounds on different sides of a person's head, the muscles are actually going to fire to try and turn the ear towards the side that the sound is on. So they still are functional, they just generally can't actually move our ears any longer. So kind of an interesting leftover that I just wanted to let you know about.